Last episode, we ran the evaluate library and watched 4 clean bars come up: accuracy, precision, recall, F1, all sitting around 0.97 on our sentiment model. But here's the thing, nobody tells you when you celebrate that F1. To get it, episode 6 retrained every single weight in the model, all 110 million of them, every gradient, every optimizer state, every saved checkpoint, full size. That's fine on a toy run, but the moment you fine tune a real model on real hardware, that cost is what hurts. So today we ask a slightly cheeky question. What if we could hit that exact same F1 but only train a tiny sliver of the weights and freeze everything else? That's LoRA, and PEFT makes it about 4 lines of code. Start with the problem, plainly. A full fine tune touches the entire network. When you call trainer the way we did in episode 5, every one of those 110 million parameters is marked trainable, gets a gradient, and gets an optimizer moment stored alongside it. So your memory bill isn't just the model, it's the model plus its gradients plus the optimizer state, often 3 or 4 times the model size. That's the wall everyone hits. Now the key idea behind LoRA, and it's genuinely elegant, instead of nudging a giant weight matrix directly, you freeze it completely, don't touch it, and you bolt on a tiny detour beside it. That detour is 2 skinny matrices. One squeezes the signal down to a tiny inner size, the other expands it back. The big matrix stays frozen, only the 2 skinny ones learn. At the end, you've trained 2 postage stamps instead of repainting the wall. Why is that so cheap? Because of the shapes. Take one attention weight matrix, say 768 by 768. That's about 590,000 numbers. LoRA replaces learning all of those with an A matrix of 768 by 8 and a B matrix of 8 by 768. Add those up and you get a bit over 12,000 numbers for that one spot. The inner size, that 8, is the rank, the famous R small r, tiny detour. And it really is just an addition. During the forward pass, the frozen matrix does its normal thing, the little detour does its thing, and the 2 outputs are summed. The model sees one combined result. There's a scaling knob called LoRA alpha that controls how loud the detour speaks relative to the frozen path. Think of it as the volume dial on the adapter. Nothing about the original weights is overwritten. The detour just adds its correction on top. Here's the part that makes it practical. You don't sprinkle LoRA everywhere. You target specific layers. For a transformer, the sweet spot is the attention projections, the query and value matrices. PEFT lets you name them in target modules, and it walks the model, finds every matching layer, and wraps just those with a frozen original, plus a fresh A and B detour. Everything else in the network stays exactly as it was, frozen solid. So what actually gets trained? Only those little A and B matrices across the handful of layers you targeted. Stack them all up, and for our base model it comes to 294,912 trainable parameters out of 110 million. PEFT prints that ratio for you in one line, and it lands at 0.27%. You are training roughly one weight in every 400. And the punchline, the reason anyone bothers, is that it barely costs you anything in quality. On a task like sentiment, LoRA lands right on top of the full fine tune, the same F1 we celebrated last episode, around 0.97, give or take a rounding error. Same accuracy, a fraction of a percent of the trainable weights, and an adapter file you can save in a few megabytes instead of a few hundred. That's the whole pitch. Let's go see it in code. One file, 3 pages. We load the base model, wrap it in a LoRA config with PEFT, print the trainable parameter count, then hand the wrapped model straight to the same trainer we already know from episode 5. Nothing new there. The trainer doesn't even care that it's a LoRA model. Page 1 is setup and data, and it should feel familiar by now. We import auto tokenizer and auto model for sequence classification from transformers, plus load dataset and the metric. We pull a small slice of the IMDb dataset, tokenize it with map, and load the same distillable base uncased checkpoint with a 2-label head. This is the unmodified full-size model, 110 million parameters, every one of them trainable, exactly the thing we want to shrink. Page 2 is the heart of the episode, the LoRA config. We import LoRA config and get PEFT model from PEFT. We build a config that says the task is sequence classification, set the rank R to 8, set LoRA alpha to 16, name our target modules as the query and value projections, and add a touch of dropout. Then one call, get PEFT model config, returns the wrapped model. We immediately call print trainable parameters on it. And that's the line that prints 294,000 out of 110 million, 0.27%. That single number is the whole point of the episode. Page 3 is the training run, and it's deliberately boring. That's the magic. We build the same training arguments and trainer from episode 5, pass in the PEFT wrapped model instead of the plain one, and call train. Because everything except the adapters is frozen, this run is lighter on memory and the saved checkpoint is tiny. We finish by saving just the adapter with save pre-trained, which writes a few megabytes, not a few hundred. And that's LoRA in one sitting. Freeze the giant, train 2 postage stamps, and walk away with the same F1 for 0.25% of the trainable weights. We shrank what we trained, but the model itself is still 110 million weights, sitting in memory at full precision. Next episode, we shrink the model itself with quantization, loading it in 8-bit and 4-bit, and watching the memory footprint fall.